Hello YouTube. So in this lecture 6, I'll be covering autonomous equations, and I'll be only covering 3 types of autonomous equations here. And I'll record a lecture 6.5 where we apply and solve problems with these equations. But in this lecture, I'll just cover what they are and classifying them and how their graphs look like. So first of all, what is an autonomous equation? Well, an autonomous equation is where the rate of growth of a population, or I guess the rate of change of y, is completely independent of t. It's just dependent on y. So for example, if we have dy dt equals y squared, doesn't matter where t is at, it just matters what y is. So the growth of the population would just matter completely on what y is. T doesn't matter in this case. And if you think about it, the way populations grow, like if you have, I don't know, human growth in 10,000 BCE versus, I don't know, 2000 AD, it doesn't matter what time it is. If you have equal amount of resources, it'll grow at the same rate because time doesn't really matter in terms of population dynamics. Okay, now let's just cover the 3 types of autonomous equations we'll be covering. So the first one is exponential or exponential decay. So if you just look at this differential equation, it's rather simple, and just solving it using separation of variables or other methods that we'll figure out in later videos, we get y equals e to the kt power. So the way this graph will look like, if we just draw t versus y, it's that if we have like a starting population of y0, it'll just increase exponentially or decrease, or if you're doing exponential decay, actually let me just draw this graph, scale this up a bit more. So if you start out here, y0, exponential decay is going to cause this to grow like this. You've learned this in algebra 2. And if it's going to be, if k is negative, so if k is negative, this is if k is positive, and if k is negative, then it's going to undergo exponential decay. So this is if k is less than 0. So this is exponential. Okay, so now let's cover what a logistic autonomous or a logistic differential equation is and what that entails. So if you just look at the logistic differential equation, it's considerably more complicated. So we have this k, which is just another constant, very much like the kt up here. We have y, 1 minus y over L, where L is carrying capacity. So the solution of this differential equation, you can use various techniques. So this involves separation variables again, and then it involves partial fraction decomposition. What you'll end up with is this equation, where c is just a constant that you'll have to determine through initial values, because this becomes an IVP if you actually have initial values. So basically what this is if you have, say, a population that's growing, so you have ty, it starts out at, I don't know, it could start out at y0. It could start out here. And basically there's a threshold, which is L, or carrying capacity. So if this was a population of, I don't know, monkeys, for example, the habitat can only sustain an L amount of monkeys. So if you start out, I don't know, above the carrying capacity, then there won't be enough resources to sustain all these monkeys. So the trajectory will kind of approach the carrying capacity. So eventually, all populations will approach carrying capacity unless you're at 0, in which case you won't ever go anywhere because there's no monkeys to reproduce. So you'll just stay at 0 the whole time. But if y0 is below the carrying capacity, well then that means that there will be enough resources for this to go undergo exponential growth, but then as it approaches the carrying capacity, resources start to run out and you start having a flatter slope. So then it'll just approach the carrying capacity, just as the one on top does as well. And then same thing if you start out below here, you have exponential growth, and then you'll just have a flatter slope. So that's what a logistic differential equation is, and it makes sense because if your y is close to L, then this derivative becomes 0. But then the thing is, when y is considerably less than L, then this ky term makes more of a difference than this term over here. So all these numbers make sense. Okay, so now let's just cover what a threshold differential equation is, and then that's enough for today. I'm recording this at 3 a.m. right now, so it is pretty darn late. So I'll just finish this off. So logistic with threshold. So logistic with threshold, very much like the logistic differential equation that I just covered. It has a maximum carrying capacity. So this is y, this is t. But in addition to a max carrying capacity, there's also a minimum that it must have. So say you have like a point here. Well, it's going to approach the logistic curve, or it's going to initially have exponential growth because there's enough resources, but then it's going to kind of just go to carrying capacity. However, there's also a threshold as well, where if you don't have enough of a population, like for example, let's say this is also another population of monkeys. Well, if you don't have enough monkeys to kickstart the population and reproduce to get into this golden zone, then you're just going to die out because there are not enough monkeys to reproduce and to allow the population to thrive. And also, if you start off with too many monkeys, so these are all different initial values that you can start off with. If you have too many, it'll just approach the carrying capacity. So any initial values that appear in this range, so like in between t and L, it'll just approach L. All these trajectories just go to L. And anything above L, y0 is greater than L, then they'll just all go to L. Anything that is below t, so y0 is below t, they just go straight to 0. So if you want a graph, I'll just make a graph, or I'll make a chart for you guys. So let's see, okay, I'm not good at drawing graphs. If y is less than t, y approaches 0. If it's in between, then y, actually no, if it's at the threshold, then it's there. Or no, if it's at the threshold, then it just stays 0. Or it just stays at the threshold. Nothing changes. Y approaches L. And if y0 is greater than L, then y also approaches L. And this is as t goes to infinity. Okay, I hope you found this helpful, and in my lecture 6.5, I'll show you how to solve for these, maybe using initial value problems, maybe applications to actual populations or actual problems. Anyhow, thank you for watching. It's really late, so I'm ending this video now.